Hey everyone, today we're going to keep working with this idea of continuity, but today instead of looking at a graph like the one we have here and identifying discontinuities and being able to classify them, today we're really going to focus on what to do if we have a function in terms of figuring out where it's discontinuous and the intervals on which it is continuous. So we're going to skip this warm-up for right now and we're going to jump down here to looking at some functions. All right, so checking for continuity. So the first type of function we're going to talk about is a rational function. So whenever we have a rational function, and again, that means we're looking at something that's a fraction, the two types of discontinuities we're looking for, first would be a removable discontinuity. Remember, that happens whenever we're able to cancel factors, which really leaves us with a whole. So whenever we see that happening algebraically, we know that we're going to have a removable discontinuity. The other thing we have to look out for is an infinite discontinuity. Right? We know this has to do with a vertical asymptote. So this is going to happen wherever the denominator is equal to 0. And again, that's because we would have a vertical asymptote there. Okay, so let's go ahead and look at this function here. So if I were looking at this, the first thing I'm going to do is factor the denominator here. And so I'm going to notice a few things happen. First of all, I can cancel this factor at x plus 2. Since that cancels, I know that I have a whole at x equals negative 2. So in terms of continuity, I have a removable discontinuity at x equals negative 2. Now, the other thing I should notice is here. At x equals 2, I'm going to have a vertical asymptote. So that tells me I have an infinite discontinuity at x equals 2. So rational functions I'm looking for are typically removable discontinuities or infinite discontinuities. Now, the next type of function we want to consider is our piecewise functions. And here, what we're really looking for are jump discontinuities. Okay, and so this could happen one of two, actually really one way. So the left and right limits do not match. Okay. And so again, we would be looking at something like maybe I have a function that does this. Something like that. So obviously at this point here is where we have our jump discontinuity. So let's look at the piecewise defined function that I have here. So we want to consider, obviously, since this point this function kind of breaks at 2, we want to see what's happening in terms of limits around that value. So I know I need to check, is the limit as x approaches 2 from the left of f of x? I need to check, is that equal to the limit as x approaches 2 from the right of f of x? That's the question we want to look at. So if I'm looking from 2 from the left, obviously I'm going to be at this top piece of the function. So if I plug in 2, I have 3 minus 2, which is going to give me 1. If I look at 2 from the right, now I have 2 divided by 2 is 1 plus 1 is 2. And obviously those aren't equal. So we would say we have a jump discontinuity at x equals 2 because the limit as x approaches 2 from the left of f of x is not equal to the limit as x approaches 2 from the right of f of x. Again, using that limit definition for continuity. All right, so now we're going to actually look at some functions and make sure we can pick out where these discontinuities are occurring. So get flipped over here. All right, so here it says determine whether the following functions are continuous at x equals 2. Let me see if this will focus any better. All right, here we go. So for number 1, I notice I have a rational function here. So right away I'm looking either for removable discontinuities or infinite discontinuities. So I'm going to go ahead and factor this. And I notice I'm going to cancel a factor at x minus 2. So again, that canceling indicates that there's a hole, or really a removable discontinuity. Well, let's go ahead and check now. We know something's happening there, so I'm going to check the limit as x approaches 2 from the left of f of x. I need to know, is that equal to the limit as x approaches 2 from the right of f of x? And I need to check if that's equal to f of 2. Remember, by our definition of continuity, we said the limit has to exist at that point, and it has to be equal to the value of the function. Now, we know because there's a hole there, this isn't going to be continuous, but I want us to get used to setting up these conditions to check for if a function is continuous. So as I approach 2 from the left, and I should go one step further here, that's going to be equal to x plus 2. So if I plug in 2, I have 2 plus 2, and that's going to give me 4. As I approach 2 from the right, again, I have 2 plus 2 is 4. So those are equal. The limit exists. However, f of 2, we know that's undefined. So clearly here, the limit exists, but it's not equal to the value of the function. We know it's discontinuous there because of a removable discontinuity. So we'd say discontinue at x equals 2 because the limit as x approaches 2, we do have a two-sided limit there, so I can talk about the limit as x approaches 2, but what we know is that's not equal to f of 2. And again, we know that's a removable discontinuity when that happens. All right, so let's look at number 2. I kind of bled over here, so make some room there. All right, so my first function now, or my function is a piecewise defined function. The first piece is the same as what I had over here. So I know if I factored that, that's going to be the same as x plus 2. So again, now we want to know if this piecewise defined function is continuous. So again, we're going to check at x equals 2. I know the limit as x approaches 2 from the left of f of x has to be equal to the limit as x approaches 2 from the right of f of x. And that has to be equal to f of 2 if this thing is going to be continuous. There's my conditions. Now, 2 from the left obviously is going to be this piece here, not equal to 2. And if I plug 2 in again, I get that same limit of 4. 2 from the right, again, is the same piece of the function because this is everything but 2. If I plug that in, I get 4. Now, by the way this is defined, f of 2 is 3. So now I have a value defined there, but it's still not equal to the value of the limit. So again, we still have a discontinuous function due to a removable discontinuity. So our reasoning is going to be the same. We're discontinuous at x equals 2 because the limit as x approaches 2 of f of x is not equal to f of 2. And again, that's removable. All right, so last but not least, we have another similar piecewise defined function, but now we have a new value at x equals 2. Again, the process is always the same. If I want to know if it's continuous at x equals 2, I have to check the left-sided limit. I have to check the right-hand limit. And I have to check the value of the function at that point. Again, this first function is the same one we've been working with, so I know if I were to factor and cancel, that simplifies to x plus 2. So when I'm looking at limits, 2 from the left is going to give me 4. 2 from the right is also going to give me 4. And now f of 2 is 4. So essentially what's happened here is we've filled in that discontinuity. So now I can say that, let's see, I want to be careful here, h of x is continuous at x equals 2 because the limit as x approaches 2 of h of x is equal to h of 2. So that two-sided limit is equal to the function value. All right, so down below we just have some more examples. We're just going to do one of them for the sake of this video, and we can always loop back and do some more tomorrow in class. So what we need to do here is first locate the discontinuities. We're going to classify it and then use the limit definition to explain why there's a discontinuity there. And then last, we'll identify the intervals where we are continuous. So let's look at number 5 here. Obviously, this is a rational function, so I'm looking out for either a removable discontinuity or some kind of infinite discontinuity. So let's go ahead and factor this and see what we've got. The top we can't do much with. Here I can factor out a 2. So looking at this, I know that there's going to be a vertical asymptote at x equals -2. And so that's making me think that I have an infinite discontinuity. So this is kind of the thinking I'm doing before I start looking at the limits. Now, we're going to go ahead and show our work. So we know, first of all, our discontinuity, part A, is at x equals -2. We already said that we have an infinite discontinuity. Okay, so now let's look at our limits here. So we're looking at -2. So I need to consider the limit as x approaches -2 from the left of f of x. I'm going to look at the limit as x approaches -2 from the right of f of x. And then I'm also considering f of -2. So let's see what happens. If I'm looking at -2 from the left, so that means something like -2.001, let's say. So if I plug in -2.001 plus 2, I'm going to get a small negative number here. Up top, since I'm squared, I have a positive. So if I have a positive number divided by a very small negative number, that means that limit is going to be -infinity. Now, if I'm approaching -2 from the right, now I have something like -1.999. If I plug that in here, now I have a positive. A positive number over a very small positive number is going to make my limit +infinity. Now, as soon as any of these conditions break down, we know we're done. We don't have to even look at the function value because right away I don't have a two-sided limit. So now I could say, let's see, f of x is discontinuous at x equals -2 because the limit as x approaches -2 from the left of f of x is not equal to the limit as x approaches -2 from the right of f of x. So for the last part, intervals where we are continuous, that just leaves everything but that point at -2. So our interval would be from -infinity to -2. That's an open bracket because we're not including that point. We're not continuous there. And then we'd be continuous from -2 to +infinity. Okay. So the last thing we're going to do quickly in this video, and we're only going to do one example. This is something we'll definitely talk about when we're back in class. We're going to look at some applications of continuity. Some problems that will definitely come up in the AP multiple choice test. So one of the ways in which we apply continuity is to fix a function to make it continuous. And here's what we mean. Here I have a piecewise defined function, but you can see here that I have just some constant k. And I don't know what that is. And so the problem asks us to find a value of that constant that will make the following function continuous everywhere. So I need to find, is there a value of k that would make me continuous? Well, I can see I need to focus here at 2. Because at that point, I need to make sure that the left and right limit are equal and that the value of the function is the same as the value of that limit. So I know for this to be continuous, again, I have 3 criteria. The limit as x approaches 2 from the left must be equal to the limit as x approaches 2 from the right, and that better be equal to f of 2. So let's see what we can fill in here. 2 from the left tells me I'm on this piece here. So if I were going to evaluate that limit, I know I plug in 2 for x. So if I plug in 2 for x, I'm left with 2k for the value of that limit. The limit as I approach from the right is this piece. If I plug in 2 for x, I have 2 squared is 4 times 3 gives me 12. And then f of 2, obviously, is that same piece. That value is also going to be 12. So what this tells me is that if I'm going to be continuous, 2k has to be equal to 12, which means my value of k must be 6. So we'll leave it there for today, and then we'll do some examples. The next couple examples have 2 constants that you need to find the value of. So we'll work through those in class tomorrow. See you then.